So, hello everyone, my name is Luca Andronico and I am a postdoc at Self Lab in Sweden and a co-developer of the software Vision, which is an open source software to analyze microscopy images and specifically to study biophysical properties of cells and membrane-bound vesicles in general. So in this tutorial, I'm gonna give you a few examples on how to use the .ome.tif format to analyze images in Vision. So Vision can analyze already some format which are implemented in the software, such as LIF from Leica system and LSM or CSI from Zeiss system. We are currently working on implementing additional formats, but right now you can analyze any image which is saved in ome.tif format. So if you have another format that is not implemented right now in Vision, you can easily convert into ome.tif file and then open it in Vision. And I will give you an example of this. So first of all, here I have an image which is acquired from a Nikon system and the format extension is .nd2. So what we have to do basically is just to save it as a ome.tif. So we can import it into image A. So we open the image, this is a 4 channels image, and then what we have to do simply is to save it as a ome.tif. At the bottom of the list, we give a name, we can call it the Nikon, since it comes from a Nikon system. We need to select the right format, ome.tif. Do not forget to actually write the extension already in the file name, otherwise it will give you an error. This is a bug of ImageJ that for some reason hasn't been fixed yet. So we can do save. We don't care about this, we don't care about the ROI. Now we save the image into ome.tif and we will be able to analyze it in Vision. So we can open it. Where was it? Sample images. Here it is, Nikon. And there you go. So this is the image we want to analyze, and of course at this point you can do whatever analysis you want to do on the image. For instance, let's say we want to measure the intensity distribution in this last channel, so we can select it. Our physical parameter in this case will be the intensity in the channel. We need to select also that for the masking. Maybe we can run some masking tests. Let's apply a Gaussian filter maybe to make it a bit more smoother. All right. And then we also need to adjust the binning since we're gonna measure an intensity. Let's say we set from 0,1 to maybe 6,000. It's a 16-bit image. And then we give maybe a step of 10. And then we can run the analysis. So there it is, the results from our analysis. We have a color-coded image showing the intensity in our cells, the distribution of this intensity, the beta value, the emission spectrum, and so on. So it is quite straightforward, and ideally, or theoretically, you can convert any format you like into ome.tif and analyze it in Vision software. So as a second example, I'm going to show you how to use the ome.tif format to combine multiple images into one and perform correlative analysis in Vision. To this extent, let me open 2 images in image A, and I will explain you in a bit what they are. So we can maybe reduce the size so we can see it clearly. Now, on the right window, we have a spectral confocal image. In this case, we stain suspension cells with the protein, which is a probe for membrane fluidity, and we want to measure the membrane fluidity from these cells. We have multiple channels, nothing new or difficult here. On the left window instead, we have a 2-channel image, where the first channel refers to a viability dye for live death, and we can maybe adjust the brightness so you can see that some cells actually have internalized the dye inside. So for instance, at the central one and the one at the bottom, those are probably dead cells. The second channel in this stack instead, in magenta here, it refers to the intensity coming from an Nexin-5 fluorescence labeled with Alexa Fluor 647. So a Nexin-5, it's a biomarker for apoptosis. I'm not gonna explain the biology of it, but what we want to do now is to basically combine the two stacks together and then correlate membrane fluidity from this stack of images with internalization of the viability dye and expression of PS to the other leaflet, meaning colocalization with the annexin 5 signal. How do we do it? It's quite straightforward. So first of all, we need to convert the stacks into images. So we go to the first one, image, stacks, stack to images. All right. And then we can do the same with the other one. So we select the other one, again, image, stacks, stack to image, and then what we have to do is basically convert them back into a stack. So stacks, images to stack. Okay, bam. And now we combine the two stacks together. As you can see, we append at the end of the first the spectral image the two additional channels. Now, before we save it as ome.tif file, we need to make sure that the dimensions are the right ones. Otherwise, we might run into issues with vision. So we go to hyperstack, reorder hyperstack. Now, as you can see, when ImageJ combined those two stacks together, he basically made 24 slices and one channel. Instead, we need 24 channels and only one slice. So we need to swap those dimensions. So channels will become the new slice and slice will become the channels. And you know that ImageJ reordered correctly the images in the stack because it assigned a different color for the different channels. All right, then we go File, Save As. We select the ome.tif format. We give a name, combined. .ome.tif. We need to always specify it and select the format. we don't care. And now you see it's converting and saving it as a ome.tif. Perfect. Now we are ready to do our analysis in Vision. So we open our software and we load the image. Sample images, and here it is, combined.ome.tif. All right, and so as you can see now we have the image combined. So as we said, we want to measure the membrane fluidity from the first spectral image plus the cytosol signal from the second to last channel, which is the viability dye, and we want to do colocalization with the signal from annexin 5, a biomarker for apoptosis. So we are just gonna set the measurements. First of all, we need to create the mask for the membrane. We go to membrane setting, we select the channels of interest. In this case, it's channel 1 and channel 9. We can also select both of them for the masking, and let's see what we get as a beginning. Okay, this is the mask. It's not too bad, but I want to point out that as you can see, some cells, probably dead cells or apoptotic cells, have internalized the dye, and this will be a problem when we do image segmentation, because you see we have many internal or like white areas that can be categorized as independent objects, as separate objects. We don't want that, so we need to go a step back, and maybe we can select only one of the two channels for the analysis, where the fluorescence or the signal from the cytosolic part is less. So if we look at the channel 1, which is this one, and the channel 9, which is, let's see, it's this is 12, this is 9. So from the 9 there is a lot of intensity, so probably if we just stick with the channel 1 we might be able to improve the masking. So we're gonna remove the 9 from here. We run it again. Perfect. Now you see that we removed a lot of internal signal. What we can do here, maybe we can apply a Gaussian filter of 0.5 or so. We can test the mask, and it looks much better. You see that we have a more continuous membrane, and again we can fill the holes. So remember always to fill the holes, otherwise you don't have a continuous membrane. We can remove the object, so we remove maybe these two clusters. I think setting 4 will be enough. Let's see what we get. Alright, and this is our final image. Sounds good. Now we need to set the mask for the cytosol. Okay, so we go to the second to last channel. We can also increase the contrast from this tab here. So maybe here we can, maximum value we can reassign to 20 or so, just to have an idea. All right, now we go to the cytosol settings. We enable cytosol measurement. Again, here the channel we want to measure, it's the second to last, the 23rd. The intensity we want to measure, it's just the intensity of that marker, so we can write A. Specific channel, again, only the 23rd. Let's see if we run the mask, what we get. Now the mask, you see, we almost got nothing, and this is because this object down here, it's quite bright. So probably we need to go manual on the thresholding. Maybe we can also lower the threshold. Let's see. We should be able now to get more signal from the intracellular environment, as you can see, indeed. But still, we have a lot of noisy pixels, which we can get rid of by removing objects. And so all those small pixels will be gone. Perfect. So now we have an optimal mask for the membrane and for the cytosol. Everything is ready. Just let's remember to set the binning correctly for the cytosol. So we go from 0.1 maybe to, I don't know, 60. This is quite dim, so I think 60 it's already enough. We can give this maybe 0.2 or something like that. Alright, and then we need to remember that we want to do object detection and membrane profiling, but also we want to colocalize with the channel 24th, which it's the channel for the apoptosis, biomarker for apoptosis. Alright, so having said that, we can run the analysis. Perfect. Now the software has finished. We can jump directly maybe to the object results, so we can visualize the results for individual objects. And there you go. So the software has identified 5 different cells. And then if we highlight each of them, we will also see the corresponding plots. This is the object number 1, the cell number 1. We have a distribution of the membrane fluidity, the emission spectrum, and the phasor plot. And we can also access the cytosol, if any signal from the cytosol. In this case, we didn't have any signal from the cytosol because these cells are quite healthy, so they did not internalize the viability dye. And we do observe profiled membrane, so we can actually see how the membrane fluidity changes along the membrane per se. And the red curve here indicates the signal on the last channel, which is the channels from where we measure an Exin5 signal for apoptosis. And as you can see, it's basically noise. There's no signal in there. And we can clearly see it if we go back we can actually see it from the full image analysis. Or let me see, I might have actually the merged image, so we can maybe look at it. Exactly. So the object number 1, so the first cell actually didn't have any signal, neither from the live dead dye, so the viability dye, the green one, nor the apoptosis sensitive dye, the magenta one. So as expected. But then if we look at the object number 2, so the second cell, you see that now the membrane fluidity decreased quite a lot. And if you look at the colocalization, we have a strong colocalization with the last channel. And this is visible already if you look at the merged image. As you can see, we have some dots along the membrane, which correspond to accumulation of an Exin5 at those areas. And we can see it in the profiled trajectories. And for this image, we also have signal from the intracellular environment coming from the viability dye. So if we look at the cytosol, there it is. And that's it. So as you can see, it is quite straightforward also to combine different images acquired under different settings of course, of the same field of view, and then you can perform correlative analysis, multidimensional analysis, and correlate membrane fluidity with other properties of cells.